All right, the last one was real short, but this one's going to be a lot longer. This time we're talking about Faraday's law of induction and Lenz's law. So first off, we saw on the last thing with that iron donut how inducing a charge through something, which will make a magnetic field, can then make a magnetic field which induces a moving charge. So what were the observations that Faraday made? So he saw that when you have a faster change in the magnetic field, that you induce a greater electromotive force, and as a result, you get a higher current. He also saw the electromotive force that you get is proportional to the area of the loop that is generating the magnetic field. He saw that the electromotive force is affected by the angle between your magnetic field and the area, so whether or not the loop is lined up with it so that the magnetic field is going through it, or whether it's perpendicular to it. And then finally, he came up with a new idea called magnetic flux, which is measured in the units Webers. And magnetic flux measures the total magnetic field through an area. So when we come down here to look at the formula for it, your magnetic flux is going to be equal to the area times your magnetic field times cosine theta. So if they're lined straight up with each other, you're not going to get any flux. But if it's perpendicular to it, then you're going to get flux, which is hopefully what we see here with why we use cosine instead of sine. So when it's completely perpendicular, we just get AB. Make sure we have our vector arrow on there. So when we look at Faraday's law, they came up with a way to determine how much EMF you're going to make, and it's equal to negative N, and it's going to be the, hold on one second, the change in your flux over your change in time. Now that negative sign is going to be helpful for determining direction, but the way I do it is I forget it, and then I just use the right-hand rule to determine it. N here represents the number of loops, which makes sense. The more loops you have, the more electromotive force you're going to be able to generate from that change in magnetic field. Now, Lenz's law says, and this is why we generate the current, that your electromotive force is generated to resist a change in your flux. Nature does not like it when you change the flux inside of a loop. And so anytime that you go to change a magnetic field inside of a loop, nature's like, nah, don't want that. So it'll generate its own magnetic field inside to try and cancel that out. And as a result, the way that it does it is, or I shouldn't say as a result, to do that, it has to generate a current in a way that will create a magnetic field that is going to resist it. So what are the ways you can change flux? The most obvious way is to just squeeze the loop. So if I have a loop, it's got a magnetic field through it, and I go and I flatten it down, it's going to have a change in flux there. So you can just change the area of it, and that's going to change your flux. The next way is to change the angle. So the angle between the magnetic field and the angle between the magnetic field and the loop. Now, in reality, it's basically the same thing as changing the area, because the magnetic field, let's say it's coming right at you out of the screen you're looking through. If I move this, if you look at the size of the area of my hand and I just rotate it, to you, all it looks like is the area of my hand is getting smaller. So it's basically the same idea, but for practical purposes, you can rotate the loop. That's something different. And then finally, you can change the magnetic field, which hopefully, when you look up here, or look over here for flux, you can see those are the three variables that are going to affect it. All right, let's do some practice problems with these. On this first one, we have a wire here, and it's a square with a 5 centimeter side. So it's 5 centimeters on this side, 5 centimeters on this side. We have a magnetic field through it with a strength of 0.16 Tesla. All right, and now I want you to tell me what is going to be the flux here when it's just sitting perpendicular to the magnetic field. Tell me what it's going to be when I take it to a 30-degree angle. And then I want you to be able to tell me what it's going to be if I take the loop and I start at perpendicular and then I rotate to 30 degrees. The resistance of the wire is 0.012 amps, and I do it in 0.14 seconds. Go ahead and give it a shot. If you're not sure, you can just let the video play. If you want to try it out, which I'd recommend, go ahead and pause the video, and we'll be back in just a second to go over it. All right, let's go ahead and take a look at it. So right here, since we are perpendicular, we don't have to worry about our cosine term. So I just take my magnetic field strength and I multiply it by my area. Since I have a side length of 5 centimeters and it's a square, I just square it. And I get 4 times 10 to the minus 4 Webers. Now, when I take it to a 30-degree angle, I need to put in cosine of 30. And when I do that, I get 3.46 times 10 to the minus 4 Webers. This is where it gets a little more difficult. How do we find current? Well, current is voltage over resistance. We got resistance. We need to find our voltage. In this case, it's going to be our EMF, the electromotive force that is induced by the change in magnetic field strength, or the strength, relatively speaking, as it starts to rotate. So we're going to have to use Faraday's law here, and we're going to solve for the electromotive force over the resistance, because that's going to be voltage over resistance. We only have one loop, and as we have one loop, we just have to put a 1 in there. We do the change in magnetic field strength, or I guess our magnetic flux, take it over the change in time, and then we take all that over our resistance. And when we do, we get 0.0032 amps. Now, we needed to determine what direction the magnetic field would be in this, and the way we're going to have to do that is using Lenz's law. You can come back and try it out on this one, but we're going to have some more practice in just a second. So with Lenz's law, you always have to have a closed loop. Otherwise, this isn't going to work. You can't induce a current into something unless the charges can flow. And then next, we need to have an external change in flux for this to happen. So we got a loop. Our flux is changing. What we need to do is find what the change is. This is going to give us our magnitude for it. Then we need to find the magnetic field from the induced current. And the way we do that is, if our flux is getting smaller, if our flux is decreasing in value, then our loop is like, I don't like that. And it's going to create a magnetic field in the direction it's already going to try and keep the flux change to be 0. Down here, if our flux is increasing, then it's going to be like, oh man, I don't like that it's going up, and it's going to create a magnetic field in the opposite direction the magnetic field is already going, so that it can prevent the flux from changing. The universe does not like it to be fluxed up. Ha. And then down here, we're going to use the right-hand rule. So once we know the direction we need to make a magnetic field, we'll just use the loop rule for our right-hand rule and find out what direction the current is. So I'll stick my thumb in the direction I want to generate a magnetic field, and then I'll use my fingers to determine what direction the charge is flowing. So what does that mean? Well, let's come over here and figure it out. Let's do a practice one here. I've got a magnetic field that's sticking out of the page, and I've got a loop of wire, and I'm going to pull that loop this way. It's going to stop being around there. So what's happening? I'm decreasing my flux because now I don't have as much magnetic field inside of my loop. When I pull this over here, the field gets weaker because it's now not the whole way inside of the loop. So my loop says, I don't like that change. I'm going to make my own magnetic field so that I can remain constant. That means it wants to make magnetic field in the way it's already going. Down here, we're looking at this. Our flux is decreasing, so it wants to create a magnetic field in the direction it was already going. So I'll put my thumb out here, I'll wrap my fingers, and that shows me the direction of current. So in this one, I would have a current that is flowing counterclockwise. Let's try one more together, and then I'll have 3 for you guys to do on your own. In this one, I've got a loop. It's shrinking down to become smaller. In that case, we look at our equation to find our flux, BA cosine theta. Cosine's not changing, B is not changing, but our area is definitely changing. So because our area is getting smaller, that means our flux is getting smaller. We want to make more magnetic field to cancel that out so that our flux doesn't change. Well, the magnetic field's going into the page. We want to create more of that, meaning my thumb's going to stick in, I'll wrap my fingers, and in this case, I'm going to get a clockwise rotation. Now, I want you guys to go ahead and try and solve for the other 3 that we have up there. In this first one, we've got a loop. Imagine the loop is completely flat with the page. It's hard for me to show that. The south is below it, and I'm moving the south end of a magnet closer to it. In this case, they're in the same plane as the page. So I have a flat loop on the board, and I have a magnet, and I'm bringing it closer, north end of it. And in this one, I have a magnetic field pointing this way, and I'm spinning my loop. It starts out so that the magnetic field is not going through any of the loop, and as I rotate it, more and more is going to go through the loop. So go ahead, try those ones out on your own and see if you can get them. All right, let's see how you did. So in this one right here, we've got a loop that goes like this. We got a magnet going up, Remember, magnetic field lines point from north to south, so we'll have field lines pointing down into the loop. As I move it up, you're getting closer to the magnet. And remember, magnetic field lines get stronger the closer they are together. They're far apart, further away from the magnet, closer together right near the South Pole. So we're getting an increasing amount of magnetic force pointing down. I don't like that change. My magnetic flux is going up, so I'm going to cancel it out by pointing upward, which means I'm going to have to rotate my fingers like this. So I'm going to get a loop that looks something like that. Imagine this side's closer, that side's further in the back. Now let's take a look down here. Since it's in the same plane as it is parallel with the magnetic field, meaning there is no flux change. No matter how close you get it, this loop is blind to that magnetic field. So no matter how close it gets, it's never going to have anything. Now over here, I've got no flux to begin with, and as I spin it, it's going to be increasing, pointing that way. So I'm not going to want that. That's increasing my flux, so I want to make a magnetic field this way. And when I do that, what it's going to do is create a current that's going to rotate it around it this way. So as we start to rotate it, it's going to come up over the top towards it. And it will do that all the way until it gets to here. And then once it's at this point and it starts to go back, the current will reverse because then the flux will be decreasing. Now let's take a look down here at this one. Let's imagine I've got a wire and my current is flowing this way and it's increasing over time. In this case, I've got a wire with a current flowing this way and it's decreasing over time. And in this last one over here, I've got a loop wire. So these three are separated. Let me draw that so you can see them. In this one, I've got a constant current. I want you guys to be able to tell me what's going to happen in each of these. And I'll give you a hint. You're going to need to use the right-hand rule twice. So you do your best, solve for it. We'll come back together, see what you get. All right, so let's take a look. In this one, I've got right-hand rule, current's going that way, magnetic field's going this way, so I've got magnetic field pointing out of the page above the wire, meaning I've got magnetic field pointing out of the page in this. Now, over time, that field strength is going to increase because it's proportional to your current. So I get more and more current, I'm going to want to resist that. So I want to make a magnetic field that points into the page to cancel it out so that my change in flux is resisted. Stick my thumb into the page, rotate my hand, I get a clockwise rotation. In this case, just like before, bottom side is going to have field that goes into the page. So it's into this loop, but over time, into the loop is going to weaken. So I'm going to want to create more magnetic field to resist that change in flux. So I point my thumb in just like before, and I end up with a clockwise. Now in this one, it doesn't matter which direction the current is going because there's no change in magnetic field. There's no change in current, no change in magnetic field strength, meaning there's going to be no change in flux. So on the last one, there's going to be no current induced. And that's all we've got for this section of notes.